Okay, so here we have problem 3, or example 3, section 4.3 to 4.4. So we're still looking at indeterminate axial loads. And again, all we're considering are those axial, like we're looking at two force members, just axial. We don't have shear, we don't have moment, we don't have torsion. So we have a load of 2,000 pounds. It's to be supported by two vertical wires for which we have a yield stress given. Originally, AB is 60 inches. And AC is 60.04 inches. Determine the force developed in each wire after the load is suspended. Cross section is given and E is given. I love it when everything's given. So if they were the same length, then we could probably assume by symmetry because they have the same area and material. If they were the same length by symmetry, we could say they have the same internal force. But if you have one that's shorter, and if you envisioned one was way longer, okay, so it's like coiled on the ground, as I'm starting to pick up that load, this shorter cable, the shorter cable is actually having to stretch and stretch and stretch and stretch. We have to have enough stress to stretch it till it's the same length, and then they'll be stretching together. Okay, so it's kind of not composite behavior until we get to the same length, and then they both pick up. So let's start with what we always start with, which is equilibrium. Okay, so we have this kind of round force here, and we are told it has 2,000 pounds. So we're going to go ahead and write 2,000 kips because everything needs to be in terms of kips and inches. And then we've got that force in cable AB. We've got that force in cable AC, and we can sum forces in the y direction. So I have FAB plus FAC equals 2 kips. Because that was going down, it was negative, so it actually equals 0. But anyways, so that's the first thing we have. Now we have to look at compatibility of deformations. So we have this cable AB, which is shorter than cable AC. So we're going to stretch, and then all of a sudden they're both going to start stretching. And so A is going to end up down here at A prime for both of them. So let's just put that C right there. And I'm going to get some little correction tape and cover that nonsense up because I don't like that right there. Okay, so we've loaded it and everything has kind of stretched to this length. So let's look at our deltas. So if I look at delta AB, okay, this is delta AB. That's the full length of AB that stretches. If we look at AC, okay, AC is only stretching this amount. And I know that this gap right here is, what did it say it was? It is a difference of 0.04 inches. Okay. So I can look at this and I can see that delta AB plus 0.04, okay, plus delta AC, not plus, they have to equal. Holy cow. What's going on with my brain tonight? I can see that delta AB equals delta AC plus 0.04 because we have to stretch delta AB down 0.04 and then they're going to stretch the same, okay? But you can see visually delta AB equals AC plus 0.04. So what is deformation? What is delta? It's PL over AE. So let's plug that in. So if I have delta AB, that's going to be the force in AB, the length of AB, the area of AB, the E of AB equals 0.04 inches. Force of AC, length of AC, area of AC, E of AC. And all of that was given except the forces, so force of AB. And then the length of AB is 60 inches. Area of AB is 0.02 inches squared. And then we have 29 times 10 to the third KSI. equals 0.04 inches plus FAC, 60.04 inches, that's our length, divided by 0.02 inches squared, 29 times 10 to the third. Okay, so we're going to simplify, and what I'm going to do is I'm going to multiply the whole thing by the reciprocal of this. So this will go away, and then it'll be multiplying 0.04 by that value. So I have 0.02, I have 29 e to the third is 580. So if I multiply this by 580, it goes away. Same with that, times 0.04. So I now have that 60 FAB, okay, equals 23.2 plus 60.04 FAC. And if I come back here and rewrite FAB, okay, equals 2 minus FAC. So we can plug this in 1 and 2. So 1 is FAB equals 2 minus FAC. 2 is 60 FAB equals 23.2 plus 60.04 FAC. So now we're going to plug stuff in. So I have 60, so we're going to go 1 into 2. 60 times 2 minus FAC equals 23.2 plus 60.04 FAC. So I have 120 minus 2 FAC, not 2, that would be 60. 60 times 2 is 120, 60, here we go, 60 equals 23.2 plus 60.04 FAC. So I'm going to subtract over here. So I have negative and then 120 plus. So I have a 96.8 equals, that's going to be positive as we come over, 120.04 FAC. So multiply by the reciprocal. So we're going to take the reciprocal of that, of 120.04 reciprocal, and then multiply, and I get FAC equals 0.80639. Well, that's very, very tiny, so let's put it back into pounds, and I get 806.4 pounds. And if this is 806.4 pounds, okay, I can subtract that if I put it back in kip form from 2, and FAB equals 2 minus FAC, which is 2 minus 0.8064 kips. So FAB equals, change signs to plus, multiply by 1,000, 1193.6 pounds. So I get FAC equals 806.4 pounds, and FAB is quite a bit larger at 1193.6 pounds. Now, one thing that we need to do is we need to make sure this is valid. We need to check yielding. So let's check yielding. Okay, and when I'm checking yielding, what I need to do is check the larger value of FAB. So let's make sure that the stress of FAB is less than yield stress. So that's going to be 1193.6, but we need to put it back in kips because it needs to be in KSI. So 1, 2, 3, so 1.1936 kips divided by area, 0.2 inches squared, 0.02 inches squared, needs to be less than 70 KSI. Okay, so 0.02 divided by 1,000. 1.1936, enter, 0.02 divided by, and I get 59.68 KSI, which is indeed less than 70 KSI. If it was not, we'd have to go to the alternate method of using a stress strain chart. So there we have it. Easy peasy.